Hey, it's Dr. J. I'm here in the Learning Glass studio with one problem that I've received several emails about. And it's a little tricky, so I decided to devote this time to this particular problem. So we're going to find all the complex, real and non-real, zeros, and then factor completely. So here's our polynomial. It's fourth degree. It has some good things and bad things about it. The good thing about it is the leading coefficient is 1. So that means that when we do our trial and error or synthetic division, we don't have to mess around with fractions. We can just use positive, negative integers. So we can look at the last term here, the constant term, and make our list of possibilities. These are our possible rational zeros. This is just a list. It doesn't mean that they're necessarily going to work, but it gives us a starting point to start trying. So we're looking for factors of 40, and then normally you would divide by the leading coefficient, but since it's 1, we can skip that and just look at the factors of 40. So 1, 2, not 3, because 3 doesn't go into 40, 4, 5, 8, yeah, 6 and 7 don't work. What else? 10, yeah, 20, and 40. And I usually stick to the smaller numbers in the list. I rarely ever, use up all these possibilities and end up having to try any of the larger numbers. But I still put them as a possibility. It could happen. Not very likely, but it is possible. There's a couple things you can do before you start doing the trial and error. And again, that's up to you. If you've got all the time in the world, you could just sit there and one by one try every single number. You can do what's called the one test. Testing if 1 works. It works enough of the time, that's worth trying. Remember, the one test is where you add up all the coefficients, and if you get 0, then you know that 1 is going to work. Let's do that very quickly. 1 minus 4 is negative 3. Plus 14 is 11. Not looking good. 11 minus 40 is, what's that, negative 29. And then negative 29 plus 40, it's not 0. So you could stop there. Doesn't really matter what it is. I guess you could write it down if you wanted to know what it was. But as long as it's not 0, that sort of saves my screen here. I have a limited amount of space. I'm not going to bother trying 1. Another thing you can do is the rules of signs, Descartes' rules of signs, which I illustrated in one of my longer videos. You count the sign changes, and that gives you an idea of what's going on. So you've got 1, so it's changing from positive to negative, that's 1. It's changing from negative to positive, that's 2. It's changing from positive back to negative, that's 3. And it's changing from negative back to positive again, that's 4. So there could possibly be 4 positive real zeros. Or there could be 2, or there could be none. Right? So remember, you count, and then you say, well, that's the maximum number, and then you drop down by multiples of 2 to get all the possibilities. But just keep in mind, there could be 4 positive numbers that work. All right. You can also do the negative zeros test. Descartes' rule for negative zeros. You replace all the x's with negative x. And I showed you how to do this the long way, but there's also a trick to it if you're doing it mentally. All the even powers will remain the same sign. They won't change. But all the odd powers will change. That one will remain the same. This one will change. And the constant term always remains the same. So this is to predict the negative zeros. I rarely ever do this, I have to admit. I think I mentioned this before. I normally test the positives first, but I'm glad I did it this time. Look, there are no sign changes. Look, positive, 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 positive. It never changes sign. So if there's no sign changes in f of negative x, that means there are no, or 0, negative real zeros. I'm glad I did that now, because now in my list of possibilities, I can erase the negatives. So I've just saved myself a ton of time, because honestly, I was about to try -1, and I would have wasted time. I was about to try -2, and -4, -5. And you've probably experienced this, where you try multiple numbers and none of them give you 0 and you get frustrated. So by using some of the rules, some of the theorems, and this is Descartes' rules of signs, I saved myself a little time. All right, I am going to have to erase this because I need the space. I also am going to erase it so I don't accidentally use this as my polynomial. That is one of the dangerous aspects of Descartes' second rule. The negative rule is you change the polynomial and then you might accidentally try to factor or solve the wrong one. Remember, this is our original problem here, so that's the one that I'm going to solve. I'm not going to try any negative numbers. All right, now I just kind of wasted a lot of time explaining the strategy. Again, these are just suggestions. If you don't want a strategy, you don't necessarily have to have one. Or you could create your own strategy. One strategy is just to dive in and just start trying numbers until something works. That's sort of the exhaustion method, where you just try every single number until something works. I'm going to only try positive numbers. Remember, I already tried 1. We did it mentally, so I'm going to go right to 2, see if that works. I have debated this with friends and other mathematicians and sometimes even students who challenge my methods. And they say, well, in all the time that you just wasted talking about it, I already found the answer. And that's fine. I'm here to share all points of view, including ones that don't necessarily agree with yours. So 1 plus 0 is 1. 2 times 1 is 2. -4 plus 2 is -2. 2 times -2 is -4. It's looking pretty good. 14 and -4 is 10. 2 times 10 is 20. -40 and 20 is -20. 2 times -20 is -40. Winner, winner. Yeah, we got one. All right, so let's keep that, save that for later. And remember, when you get a non-zero remainder, then you have to start over, or at least start over with where you last were. When you do get a 0 remainder, you don't have to start over. You can keep rolling. All right, so add another row here and try another number. All right, let's try 4. So 4, 1 plus 0 is 1. 4 times 1 is 4. -2 and 4 is 2. 2 times 4 is 8. 18. 4 times 18 is 72. So -20 and 72 is 52 is my remainder. So it's not 0. Yeah, it's not 0. However, there's another rule, all right, or another theorem, or another law, however you want to think about it. If all of these are non-negative, yeah, the entire row, now I guess you could say if they're all positive, but you really can't say that because 0 could appear in this row and you would still say it's non-negative. So there's an intentional usage of the word non-negative as opposed to just saying positive. But mentally, if you see a bunch of positive numbers, that's the same thing. It's all non-negative, all right? Then that means this is called an upper bound. All right, an upper bound is like a ceiling, or it's like an end point in which you will never find a 0 beyond that point. It's like a fence. It's saying all of the zeros lie before this number, in particular 4. So that is really cool. If you have an upper bound, we'll say UB, 4 is an upper bound, that means I'm not going to try any of these numbers. Don't even bother trying any of those numbers. All right. I like this pen. I think I'm going to switch to this pen. I hope you like it too. All right, so that means we have to try numbers smaller than 4. All right, now remember, 1 isn't going to work. 4 doesn't work. None of the negatives are going to work. I'm stuck trying 2 again. I don't have any other choice. All right, so we'll go back to here. This was the last quotient that resulted in a 0 remainder. So that's 1, -2, 10, and -20. Try 2 again. All right. I mean, we've exhausted every other possibility. So it's like we have only, this is our only hope, is to try 2 again. We know that 4 didn't work. It's an upper bound. So it doesn't work. It's not a 0. And nothing past 4 will work. So we've got to back up to 2 again. All right, let's do it. 1 plus 0 is 1. 2 times 1 is 2. -2, +2, 0. 2 times 0 is 0. Looking pretty good. 10 plus 0 is 10. 2 times 10 is 20. Yay, it worked again. It works again. So that means that x equals 2 is a 0 of multiplicity multiplicity 2. In other words, x minus 2 squared is a factor. All right, I hope that's coming up. Yep, looks pretty good. All right, so let's hold on to that. I guess we were saving it over here, but now I have it over here. So it's occurred twice. All right, and then our last step will be to pull this out of the quotient, turn it into a quadratic equation. Yeah, that's your x squared term, that's your x, and that's your constant. I would probably just rewrite it like this. Yeah. Remember, when you're finding a 0 means setting the equation equal to 0. That's what a 0 is. It's a solution to this equation. You could use the quadratic formula if this was a more complicated equation. I would use the quadratic formula or some other more sophisticated method like completing the square or whatever. Factoring sometimes works. This is a very simple one because the middle term is 0, so I'm just going to use good old-fashioned solving for x technique. It's called the extraction of roots method. You take the square root of both sides. Now this is a negative radical, so it's going to be I square root of 10. And don't forget, there are 2 possibilities, negative I square root of 10. Remember that theorem about conjugacy, right? Square roots, imaginaries, they always occur in pairs. You always have the plus or minus possibility. All right. So there you go. Those are your zeros. I hope that helps explain when this happens. It doesn't happen very often that you have to try the same number again, but when you've exhausted all your other possibilities, you don't have much choice. Let's go ahead and list the final answer here. So the zeros are just the x's. So we got 2. All right. Now technically it occurs twice. Yeah, but when you write it out, you just write it once for the zeros. There's some disagreement with that philosophy. There are some folks that say, no, you have to go 2, comma 2. You have to say it twice. I don't require that. I do require that you write the factor twice or that you use an exponent for the factor. So you could also write this x minus 2, x minus 2. I'm not going to. I'm going to write it using an exponent. And so the factorization, we call this the complete factorization because it's completely factored. That's rewriting the function f of x not as an expanded polynomial, but as a factored polynomial. I typically put the real factor first, followed by the two imaginary factors. Oh, not x, that's 10. Square root of 10. And one of them's negative, one of them's positive. And there you go. Because 10 is not a perfect square, I'm leaving it as the square root of 10. I'm not using a decimal. You could, if you're curious, put it in your calculator. You're going to get like 3 point blah, 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 blah. I don't know. I don't have it memorized, but it would fill up your whole calculator screen with decimals. So, I mean, it's not illegal, but it's just not preferred. It's preferred to write it in the simplest way, which is square root of 10. I don't know what version of this problem you're going to get. You might not get this exact same problem, but you'll get something similar to this. If it happened to be the square root of 4, or the square root of 9, or the square root of 16, or some nice perfect number, then you could do one more step and actually remove the square root. But for something like this, it's an irrational root. It's also an imaginary. I would just go ahead and stop there. All right, I said I wanted to keep this short, not something that I'm very good at, but I did the best I could to just kind of do a bite-sized video. Also gave me an excuse to use the new Learning Glass Studio, which you might be seeing more of in the future. So until we meet again, this is Dr. Jordan. I'll see you on the internet.